Hello everyone. So today we are going to look at one binary challenge from TryHackMe, and the challenge is DearQA. I have started the machine and I have also downloaded the binary so that you don't have to wait and watch me wait for the machine to start up. The challenge is pretty straightforward. We basically are given binary and we are supposed to fetch the flag from it. So to start with, let me go into a folder that I have specifically created for this, and I have the binary here, DearQA. I will remove this by cache. Okay. So now we have the binary here, DearQA. So if we do file on this, this is a 64-bit executable, and this is dynamically linked, and this is not stripped. This is a good thing. If it is stripped, then we will not find any symbols, and it's a little difficult to understand what the binary is doing. But if the binary is not stripped, that means that it will have all the symbols, and which means that it will also have all the function names, all the variable names, and everything else that we may need to reverse engineer this. But before we jump in, let's start with quick strings on this binary. Not that we are expecting to find a flag in this, but there's never a harm in doing this. So these are pretty much the standard standard functions that you would see in any in any C binary. So what we are looking for is basically how to get the flag. I don't see anything standing out extraordinary other than this string here, vulnerable. But let's not jump to conclusion, and let's see what this binary is doing. And the quickest and easiest way to do that is run Ghidra. So I will run Ghidra, and Ghidra is in repos for both Parrot and Kali. So earlier you had to go and download it from Ghidra website, but now you don't need to do that. You can just do a apt install Ghidra, and you will get Ghidra. We will just open a new project. That's what it needs. So you can give any name to project, and I'll just give AA, and open this project. Click on this dinosaur, whatever you want to call it, and then we will import the file. This is the file that we want to analyze. Right, so we'll just go to the folder where I have this, which is THM DearQA, and then this binary. This identifies that it is a GCC layer. It is a binary created with GCC, and it should automatically ask me to analyze this file, and we should be good to go. So it has not been analyzed. We just want to go with the defaults. That should be fine for us, and load it. So we can see that the analysis has finished, so we should go ahead and check the functions that we have here. So you always want to start with init function or start function or one of those functions, right? And since this is not stripped, we don't even have to worry about all those. We can directly jump into the main function, and main function will tell us where the function is starting and what it is doing. What we can immediately see is that it is just printing some statements, and then it's doing a read on something, and then local 28 is our input. So let me rename this. I'll just say rename variable, and we will say our input. So as you can see, our input is defined with a size of 32, and it is using a scanf function to read into this and then printing this. And scanf, as you know, doesn't do any binary check, which basically means that you can easily overflow the values that are being read with scanf function. Now that being said, the other function that we are seeing here and we also saw in the strings output is one. This seems to be an interesting function because the name is itself interesting, right? So you never want to miss something like this. And as soon as we open this function in the code view, we can see that it says congratulations, you have entered in the secret function, and it executes something in bash. It is basically doing a execv of bin bash and with no parameters. So basically, if we are able to execute this vulnerable function, then we don't need anything else, because that should allow us to basically get into the vulnerable function and execute bin bash. Now one thing to remember is we should note down this address here that we are seeing here, which is 0040004000686. This might become useful for us, so we'll just remember this for 00686, and when we have something useful, we might be able to use this. I don't want to save this, this is fine, and I can just exit this. Now the next thing that we want to do is basically run this. So let's run this and see if we give a name. As we expected, it prints those 3 lines that were there in the source code, and then it asks for my name, and once I give my name, it just says hello Amit. We saw that this variable that was taking the input in what's your name was just 32 bytes in length. So if we are able to go beyond 32, then we should be able to basically crash this function, right? So let's do python 3 minus c print let's say a 100 times. Should not be required, but there's never any harm. So let's do this and then copy paste this, and immediately we can see a seg fault. This is good news. This basically means that we were able to do something that the program was not supposed to do, right? So we were able to somehow break the program and come out of the logic that the program was expecting to run in. Now once we have seen that, it's just a matter of overflowing your right instruction pointer and then taking over the instruction to ensure that we can jump into the vulnerable function, which was at 4000686 hex address. Now since we have seen that, let's do a metasploit ms locate what's it called as locate create. That will be too much. Metasploit framework. So in Metasploit framework, we are looking for pattern, create pattern. That was the name I was looking for. So create pattern, no. Okay, so we can see MSF pattern create. We will give it a length of 100 that we used for crashing the program, right? So MSF pattern create basically creates a cyclic pattern. If you don't know about cyclic pattern, you can search about it. Cyclic pattern. But cyclic pattern is basically a pattern which is unique in the sense that no pattern is seen to be repeating. So once we get a crash and we see where the application is crashed, we should be able to exactly figure out where the application is crashed. Now once we have generated this, I'll run this in GDB so that we can see where it has crashed, and we will just say run, it will ask us for what's the name, and I will just give the cyclic pattern that we have created with MSF pattern create and enter, and we see that it has crashed. And as expected, we can see that the RIP doesn't have anything useful for us, but the RIP has a specific pattern which is from the pattern that we had given, right? So let's quit from MSF GDB and go to pattern search, pattern offset. We will give -q to query this, and we can also give minus length, the same length that we had given earlier, but that's not even required. So you can just give this minus L50. No exact matches. Are we a little short of the length, or should I search for this in RBP? Let's search in RBP. Where is the exact match? Okay, that is interesting. Let's try this again. We will create a pattern again, and this time let's create a pattern with 60 and run it with GDB. Run. Give this, quit, and query for what we find in RSP. We can search in RBP as well. So let's see minus L60 and then minus Q this. Am I doing something wrong? Length sets Q. Yeah, it's Q. Okay. Let's search the value that we found in RBP. Oh, okay. So let's do something interesting. Then we will do GDB init, and we will add PEDA. PEDA is there. Now since we have PEDA, PEDA itself has this built-in, so we should be able to say pattern create, and we will create a pattern of length 60. Now we can do a run and give this pattern that PEDA has generated for us, and we can immediately see that it crashed again, and again we have something very similar to what we gave in the input, right? It's something somewhere around here. That's the length where we have crashed. But now since we have done it with this, we should be able to just do pattern offset, and pattern offset we want to give the pattern, and we will again use RBP, and it is found at offset 32. What this now means is that I should be able to, let's open a new window and say python -c print a, and our offset was 32 plus let's add b so that we can identify that we are actually writing at the right place, and put 8 times b there. We will get this pattern. So let's run this again and give this, and as soon as we do this, we can see that we have overwritten RBP. Okay, now RBP is looking for RIP. We are seeing that it's still not overwritten, but that's okay. RBP and our IP should be at same place, so we should not be much worried about it. But let's see what happens if we give this the address that we had found out earlier, which was 4000686, right? So let's do that, and we will have it like uh, 86 slash x 86 and then slash x 4000686. So now what I have done here is basically change the address into Latin Indian address, and if you see, it is just the first bit in the last, first byte in the last and last byte in the beginnings, right? So 4000686, that was the address that we were looking for. Let's now give it to DearQA, and we are expecting that it should run that vulnerable function, but it doesn't. So let's try to see why it is not doing this, and for that, first thing I am going to do is write this into a file in tmpa, and we will do a XSD of tmpa. And what we see is something very interesting here, right? So we are seeing 4006686, but there is a C2 here, and this of course should not be present here. And then we also have 0A here. If you were doing it with Python 2, probably you will not face this issue, but if you are doing it with Python 3, because of how it treats strings versus bytes and all those things, this is a problem. So what you want to do for this is basically, instead of print, we want to import OS and os.stdout.buffer.write, and this will write everything as is without trying to interpret it, right? So it doesn't care about bytes and strings concept. This just prints it as a raw bytes as is into the file. Was it os.stdout.buffer.write? Let's see. Python sys.stdout, it's not OS, it's sys. So let's fix that quickly. This should be sys, and so should this be, and it requires a byte-like object, so we can just give a B here and a B here, and we have the file again, and we should be able to do XSD. And we can now see that it is doing exactly what we wanted it to do, right? So it has 32 bytes of A's and then 4000686. And now if we do a cat of temp A and pipe it to DearQA, and we should have the std and std out open so that we can interact with it, and this should work, but doesn't look like it is working. It's still waiting for something. It's probably waiting for enter or something, right? So let me give echo here and see how it behaves. Do we have ID? No, it still crashes. Okay. Okay, sorry about that. I had to quickly check on the issue that I was facing, and I figured out what I was doing wrong. So let's look at this again. Let's do that from our GDB, right? Let's again print that A's and B's that we were printing, and we will have, instead of this, let's put B's into 4, and we don't want to put it into a file. This is okay. And then gdb dot slash DearQA run. So this is what we were ideally giving, right? So the process exits, but that's interesting. Now let's again give this and give 4 more B's, and we get a crash. Right, we got a 6F, and we can see that our BP is all B's, RIP is still somewhere else. So let's run once again, and I copied something else, so let me copy that original, this one, which is 32 plus 4, 36, so 37, 38, 39, 40, and 1, 2, 3, 4, right? So let's give this and see what happens. Now we are clearly able to see that we are able to overwrite RIP, and we have the 4 4s here. 4 4s is basically D, 4 1 is A, 4 2 is B, 4 3 is C, 4 4 is D, right? So now we are able to overwrite the RIP with the address that we wanted, and so basically it means that we were actually falling short of 8 characters when we were originally writing this into our temp A file. So let me change that, and instead of 32 let us give 40, and this is logical, right? So we saw that the size of the buffer was 32, but I didn't realize that we were not crossing 32. So if you are just giving 32, it is only overwriting your null byte and nothing beyond that, so there is no way that the application will crash, right? So now let's again run this with 40, and then we have that 400686, and that we are writing to temp A, and then we will execute this command. Hopefully we do not need this echo, we might need this, but let's check. And segmentation fault, so let's do this echo as well, but still it crashes. Okay, okay, so one more mistake that we had done earlier was that we didn't realize that the address is canonical, and it's not just 4 bytes, it's 7. Actually there are 8 bytes in 64-bit addressing, but first 2 bytes cannot be used for addressing, so only 6 bytes can be used, which basically means that we cannot just use this exact command, right? This has to be 8 bytes, but this was not 8 bytes, it was only 3 bytes, and hence the address was never completed. We were going into a different address. The simple solution to that is you can use struct module. So we have done import sys comma struct here, and then struct.pack less than q. This will basically pack it as a 64-bit address, and then the actual address that we had, which is 400 and 686, and this we are putting in temp A. And once we put this in temp A, we can again do the same thing that we were doing earlier, which is cat/tmp/a and then echo and cat minus, and this time we should have shell. Now that we have done this, all that we need to do is, instead of sending it over to this guy, we can actually send it over to our IP that we have here, and we can do that with NC, and the port number is 75700. So once you do that, and I do not have ncat, I think I would have aliased it, so let me unalias it. And I am not connected to VPN. Okay, so just give me a moment. I will again start my attack box and connect to VPN, and then we will resume. Okay, I am back. So now I am connected to VPN, and we can see IP address show dev turn 0, that I am IP address. So okay, I need to run this again with sudo, I guess, so that it can add my link and create the interface. Okay, now this time it is connected, and we should have the tunnel now. Okay, now we have the tunnel, so now we can execute this command, and we should get a bash shell. So that's one way of solving it. The other way is another interesting way that I found out. So I wanted to show that to you. So there is a module called pawn tools in Python. So if you search for pawn tools, this is a very famous module for CTS and binary exploitation and so on and so forth. It has a lot of amazing functions that you can use for solving any binary exploitation. So when you install this pawn tools module, it also installs pawn. This is a command that you can see. It's in my home local bin pawn, and that is again because I have installed it with pip install pawn tools. Pip install pawn tools -- user. So when you do it with -- user, it is installing it in your local bin, right? But this also has a function for template, plate template, and then you can give the binary name to this, and you can say host is equal to we will take this host name, host IP from here, and -- port equals 5700. If my memory serves me right, yes, that is correct. And we will just remove this. It should take a moment, and then it should give you this template that you can use. Okay, so now what is interesting with this is that it gives you the option to both run it as local on the local binary or on the remote binary, remote side, right? So you can simply copy this into a file, let's say /tmp/a .py, and once this is generated, I can go into a.py, and we can do the same thing that we did in our other script, which is import sys, and then we can do io.sendLine payload, and for payload we need payload equals nothing, and payload plus equals we need is 40 types. You can do quite a lot of other things with this, but I am not going to those things today. And then we basically need the P64 0x400 686. This is the address that we wanted, right? And then we do a IO send line. Before doing this, we will have to basically do a receive line, right? And then we can do Python /temp a.py local, and somewhere we have missed this. Okay, this is bytes. So this should be bytes, right? Okay, I know. I need this as well as byte, otherwise this becomes a string, which is a problem. Okay, so now we got a shell, and this is local because we said this is local. When we were running this, we said this is local, right? But the good thing is, once I have verified it on my local system, I can just run it as is, and it should connect to the remote system, and I'll get a cell on the remote side. I don't have to change anything here. So hope that is useful for you. Thank you everyone.